Fluid dynamics is going to be the topic of this lesson in my brand new physics playlist, which when completed will cover a full year of university algebra-based physics. Now when we're talking about fluid mechanics, we're talking about fluids in motion. We first got to compare and contrast laminar flow with turbulent flow, and then we got to talk about an ideal fluid, and then we're going to kind of contrast that with viscous flow with a viscous fluid. And then we're going to get into the math, and most of the math is going to center around the equation of continuity and Bernoulli's equation. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we want to start this lesson off by first contrasting laminar flow and turbulent flow. So laminar flow, also called streamline flow, is characterized by steady fluid flow where all the fluid particles are traveling in nice, regular linear paths we call streamlines, and those streamlines do not cross. Now we contrast this with turbulent flow, which is characterized by eddy currents, kind of localized pockets where you see circular motion of the current and things of this sort, like you might find at the base of a waterfall or in the rapids of a river, things of this sort. Turbulent flow, you're more likely to find it when you have higher flow velocities or when you have rapidly changing fluid flow velocities as well. Again, like you might find at the base of a waterfall or in the rapids of a river. And we also got to define what we call an ideal fluid. Now, there's no such thing as an actual ideal fluid, but this imaginary fluid is kind of the ideal. And the more a fluid looks like our ideal, the more it's going to behave like an ideal fluid and undergo laminar flow. Now this ideal fluid has four characteristics. It is incompressible, it is non-viscous, it's undergoing steady flow, and not turbulence. And so by definition, an ideal flow is undergoing laminar flow in contrast to turbulent flow. So next we want to contrast the flow of an ideal fluid through a pipe versus a non-ideal fluid through a pipe. And what you'd find for an ideal fluid flowing through a pipe is that you'd have all the streamlines flowing independent of one another and all flowing with exactly the same flow rate, the same velocity. So, well, the key is this. Again, an ideal fluid is non-viscous. So, and viscosity is like friction between the different streamline layers. Well, in this case, for an ideal fluid, there is no friction. There is no viscosity whatsoever. Also, that viscosity also ends up displaying itself because you get viscosity with the edges as well in a non-ideal fluid. But again, the ideal fluid has no viscosity, and so we don't see that. But what you're going to see for the flow velocity profile of a real fluid is that it actually slows down closer to the edges and speeds up closer to the middle. So, and also you see that these streamlines aren't flowing independent of one another because there's friction between those layers causing them to want to flow together. Think of like molasses or honey and how all the fluid wants to flow together when you're trying to pour it and things of this sort. Same kind of thing here. You're also getting friction between the layers at the edges with the pipe itself, which is what kind of how you explain this lovely velocity profile for those different streamlines. Now, Poiseuille's law, you're probably not likely to do an actual calculation with this, although I can't guarantee it, but not likely an equation you have to memorize, but something is you probably just want to understand how the variables play out here. So it's volume flow rate, and you can see that the volume flow rate is proportional to r to the fourth. Now, I wouldn't expect you to realize that it's to the fourth power or anything like that, but you should recognize that, yeah, it makes sense that it's proportional to the radius. A bigger pipe is going to get a higher overall flow rate. So, and it doesn't just increase with r, it turns out, but r to the fourth power. And the idea is that, you know, it's flowing fastest at the middle. And as the pipe grows bigger, so the volume of the pipe is growing faster than the surface area around the edges where it's traveling the slowest. And so it's not just simply r. And I don't know that I would have predicted r to the fourth either. So, but it is not simply r, but r to the fourth in this case. Also, the volume flow rate is proportional to the difference in pressure. So from one side of the pipe to the other side of the pipe, the whole reason it's flowing is due to some sort of pressure difference. And the bigger the pressure difference, so the faster it's going to flow. So think of like when you suck on a straw. When you suck on a straw, the harder you suck, the faster the fluid flows through that straw, right? Well, when you're sucking on a straw, all you're doing is creating a pressure difference. And the harder you suck, the greater the pressure difference and the faster the flow. So we also see that there's some inverse relationships as well. So the volume flow rate is inversely proportional to eta here. And eta here represents the coefficient of viscosity. A higher coefficient of viscosity means higher viscosity. More viscosity should lead to slower flow, again, like molasses or honey as well. And so it makes sense that the volume flow rate is inversely proportional to that coefficient of viscosity. And then finally, it's inversely proportional to the length. So for a longer pipe, you're going to get more resistance to the flow, if you will, because you've got a longer run where you've got the edges and stuff like that. And so you're going to get a slower flow rate there as well. So if you were ever going to siphon gas from a car or something like this, so you'd want a short tube and you'd want it to have a pretty good radius or diameter associated with it to suck on. Now, if instead of a short tube, you used like a 100-foot long garden hose, or let's just make it a 5-mile long garden hose, if such a thing existed, and if you sucked on the end of that garden hose and 5 miles away, the other end's in your gas tank, there's no way you're getting any gas out of there. So because there's so much resistance to flow along the length of that pipe. So again, volume flow rate, it makes sense that it's inversely proportional to the length of the pipe. So now we're going to get into the little more math-intensive portion of this lesson. Some calculations you're definitely going to be on the hook for. We got to start by introducing what we call the flow rate, or volume flow rate in some cases. And it's going to have units of volume per time, so meter cubed per second, the SI unit. And in this case, it's the cross-sectional area times velocity, and it's typically brought up in the context of fluid flowing through a pipe, and that's the context we're going to bring up here as well. And so if you take a look at that cross-sectional area, so in this case of a circle for a cylindrical pipe here, and then we multiply it by the velocity, and keep in mind that the velocity is the displacement over time. And so if we take a look at that area times some sort of displacement, we'll see that it's going to map out the volume of a cylinder. And you can see that area times displacement gives you the volume, then over time. And that's why this has units of volume over time. And it's just the volume of fluid flowing per second, if you will, through this pipe. All right, now next up on the list is our equation of continuity. And this says nothing more than just that the flow rate in a pipe is constant. So in a single pipe, that flow rate is constant. I say pipe, it could be in a hose or anything like that, but the flow rate in a single pipe or hose is going to remain constant. What flows in has to flow out at exactly the same rate. The only way this could not be true is like if you're flowing this through a hose and all of a sudden it ballooned up in the middle. So before it like popped or something like that, for a brief second, what was flowing in might not be flowing out. But once it normalized again, anything flowing into that hose has to flow out the other end at exactly the same rate. So that's our equation of continuity. Flow rate in any one region is equal to the flow rate in any other region. And we're typically bringing this up in the context of a pipe that either widens or narrows like the one I've got right here. And so the idea is that the flow rate in this region is going to be equal to the flow rate in this region. And so A1 V1 equals A2 V2. Now you've got to be careful because we've got two things to talk about. We can talk about the flow rate, which is the volume per time, but we can also just talk about the velocity of the fluid, which is just kind of its translational velocity, and that's not the same thing. So it turns out when this pipe narrows right here, you're going to find out that the velocity is going to go up because the cross-sectional area is going down. So with this smaller cross-sectional area with a smaller radius, so that cross-sectional area goes down, the velocity goes up. And this is something you intuitively know. So if you've got a hose and you've got it on full blast, but you want the water to come out faster, what do? Well, you stick your thumb over the end, and what you're doing is you're actually restricting the cross-sectional area through which the water can flow. And by doing so, and making that cross-sectional area go down, the velocity of the fluid speeds up. But you got to be careful again because the flow rate has not changed at all. The water, if it's entering the hose, it's coming out the other end at exactly the same overall flow rate. But because the flow rate is the same, that area with smaller cross-sectional area does have a faster velocity. So just keep in mind the difference between flow rate and velocity in this case of that fluid. All right, you might have to definitely have to do some calculations with this equation of continuity. And in fact, I think that's where we're going to start here. So the first question on the study guide here says, a pipe with a radius of 12.0 centimeters becomes constricted, reducing the radius to 4.0 centimeters if the flow rate of an ideal fluid in the region of the pipe with a radius of 12.0 centimeters is 0.10 meters cubed per second. Question then says, what is the flow rate in the region of the pipe with radius of 4.0 centimeters? And this is really just making sure you know the difference between flow rate and velocity, because again, the velocity of the fluid is not going to be the same in the two regions, but the flow rate, according to the equation of continuity, will be exactly the same everywhere in that pipe. And it's therefore still going to be 0.10 meters cubed per second. And again, that flow rate is a volume flow rate, so it's change in volume over change in time, and is the same everywhere within that pipe. So in this question, there's no calculation to do here. You just had to realize that you were being asked about flow rate, not velocity. And again, we understand that from the equation of continuity that the velocity of the fluid is not the same in both regions, and it should be faster in the smaller region. But that wasn't the question, it was about flow rate. But the next one's going to be about that velocity. So same setup, it says a pipe with a radius of 12.0 centimeters becomes constricted, reducing the radius to 4.0 centimeters if the velocity of an ideal fluid in the region of the pipe with radius 12.0 centimeters is 2.0 meters per second. So now it's the actual velocity being given. So let's get rid of this now. Then the question says, what is the velocity of the fluid in the region of the pipe with radius of 4.0 centimeters? Now the big mistake students will make here is they'll look at this and be like, oh yeah, it's going to be faster down here in the smaller pipe. I learned that. And they look at this and they say, oh yeah, the radius went down by a factor of 3, the velocity goes up by a factor of 3. But be careful, it's not radius, at least initially, that shows up in that equation of continuity. It's the area. So in this case, what's the area of a circle? It's equal to pi r squared. And so you could look at this a couple different ways. We can plug some numbers in. We can plug pi r1 squared here and pi r2 squared, and lost my 2 there. And we could do that. So, or you can realize just some relationships here. So the area the cross-sectional area here is that of a circle, and the area is proportional to, not to r, but to r squared. And so if r goes down by a factor of 3 from 12 centimeters to 4 centimeters, well, if r goes down by a factor of 3, a is going to go down by a factor of 3 squared, down by a factor of 9, which means that the area is only going to be 1/9 in this region that it was in the big region here. And if the area is only 1/9 of that value, that means the velocity is going to have to be 9 times faster. That's the key to this question. And so in this case, if it was 2.0 meters per second in this larger region, then here V2 is going to have to be 9 times bigger than that, and it's going to have to be 18 meters per second. Now, if you didn't like that line of reasoning, and I highly recommend you're going to want to like that line of reasoning, but if you didn't, we can also just plug some values in here. So we can substitute pi r squared in for the area on both sides. And so you'll have pi r1 squared times v1 equals pi r2 squared times v2. The pi's are going to cancel. And now we can plug those radii in. We don't have to convert them into SI units. The units are going to cancel as long as we use the same units on both sides. And so we're going to have 12 centimeters squared times 2 meters per second equals 4 centimeters squared times V2. Well, in this case, 12 squared is going to be 144. We're going to divide that, well, we can do this a couple different ways actually. So we'll bring the 4 squared over, and we can do 12 over 4 quantity squared, because that's a little easier. 12 over 4 is 3, 3 squared is 9, 9 times 2 is, yet again, 18 meters per second, solving for V2. So you can do it either way, but if you understand the relationships, you can get there quite a bit faster than setting up the equation here. All right, the hardest piece of this lesson is what's up next, and that is Bernoulli's equation here. And so Bernoulli's equation can be expressed a couple different ways, and so this is one of them. The other way is simply that pressure, and this is what we call the dynamic pressure, sometimes this term right here. So, but it's the kinetic energy per volume. This is the potential energy per volume. Notice if you take the density here, which is mass over volume, and replace it with mass, you'd have kinetic energy here, potential energy here. Well, both of those have been divided by volume, turning mass over volume into density in both cases. So this is really a kinetic energy term per volume, and this is a potential energy term per volume. And these all three terms have units of pressure Pascal, which is the only reason you're allowed to add them together, right? All right, and so it's this combination of the static pressure, so the dynamic pressure, sometimes they're called, but the kinetic energy per volume and the potential energy per volume, the sum of those three terms is equal to a constant. And that's why under one set of conditions, it's equal to those same three added together under a second set of conditions. This is the Bernoulli equation, or Bernoulli's principle, if you will. All right, oftentimes you're going to see this in the context of dealing with pipes that get narrower and things of this sort, or sometimes that change levels, so there's a difference in that potential energy per volume term as well. So let's take a look at a couple of different questions involving this. So the first one here, A horizontal pipe has a radius of 12.0 centimeters in region 1. Let's make that region 1 here. Oh, let's get that 2 meters per second off of there as well. All right, so once again, a horizontal pipe has a radius of 12 centimeters in region 1, but becomes constricted, reducing to a radius of 4.0 centimeters in region 2. And actually, I put 4.00 centimeters on this question. I wanted more sig figs, but if the velocity of the water, so now we're specifically talking about water, but behaving as an ideal fluid, flowing in region 1 is 2.00 meters per second. Oh, I guess I made it 2.00 meters per second. Question is, what is the pressure difference between regions 1 and 2? Now, one of the things that makes this a little bit easier is that we've already done half of this problem for ourselves in the last question. We found out that, oh yeah, if the velocity over here is 2 meters per second, over here the radius goes down by a factor of 3, which means the area goes down by a factor of 9, which means the velocity goes up by a factor of 9. And 9 times faster than 2 meters per second is a velocity of 18 meters per second. And so we already solved for that half, which is going to make then using Bernoulli's equation just a little bit easier. Now, the other thing that makes this a little bit easier as well is that if you look at kind of the midpoint of the pipe right here, that has a certain average height of the pipe, if you will. Well, in this constricted point, because this is a horizontal pipe, it's the same average height. And so what you find then is that y1 equals y2, and these two terms are equal. And if they're equal, that's just going to fall out of Bernoulli's equation in this case, and that's pretty common. And so we've only got the 4 terms left, and so we're going to be left with P1 plus 1/2 times rho V1 squared equals P2 plus 1/2 rho, V2 squared. So this is what we're left with. And the question's asking for this pressure difference between P1 and P2 here. So I'm going to solve for P2 minus P1, call that delta P in this case. And so we're going to be left with the 1/2 rho V1 squared minus, bringing this term to the other side, 1/2 rho V2 squared. And we know all the numbers now. So we know the density of water is 1,000 kilogram per meter cubed. Let's make that look like a better 3 there. And then times the velocity. And in this case, the velocity in region 1 was the 2 meters per second. Got to remember to square that term. Then we'll subtract off the 1/2 rho V2 squared. Again, density of water, 1,000 kilograms per meter cubed. So, and then times V2 squared, which again, fortunately, we would, if we hadn't already figured out in the last question, we'd also have to use the equation of continuity to figure out before then plugging it into Bernoulli's equation here. But we already did the work for us in the last one, so that's 18 meters per second squared, and this equals delta P here. And now we got some plugging and chugging to do. Good time to pull out your calculator, but the numbers aren't terrible here. So 2 squared is 4, 4 times 1,000, 4,000 times 1/2 is 2,000. So, and units here are Pascal. And then this one's going to be fun, right? So you can do 18 squared, which might be better off in your calculator, but I believe that's 324. Half of 324 should be 162 times 1,000 is 162,000. So we'll subtract off 162,000 Pascal to get delta P. Well, 2,000 minus 162,000 is negative 160,000 for your pressure difference here. In this case, if I technically wanted 3 sig figs, I could make this negative 1.60 times 10 to the 1, 2, 3, 4. Whoop, I lost it. 1, 2, 3, 4, 5. 10 to the 5th Pascal. There's your pressure difference. Now, does it make sense that the pressure difference is negative? Well, if I'm talking of going 1 to 2 and I'm doing final minus initial, then yeah, it's going to make sense. But this is an important principle right here from the Bernoulli equation. So it shows that as you go to a constricted region, the pressure goes down. That's why it's a negative pressure change. Now this is important, but we can see it back from the original equation here as well. So again, we already realized we could ignore these 2 terms right here. But what you find then is that as you go to the narrower region, the velocity goes up. And so this overall term here, that dynamic pressure goes up. But again, which means if these two sides are going to remain equal, that means the pressure has to go down. That way, when you add them together, it's still equal to these two added together. So that's kind of the deal. When you go to that constricted region, so because that velocity goes up, the dynamic pressure goes up, which means the static pressure has to here go down. This is also an example of what's known as the Venturi effect. Let me write that guy's name down. So it's simply just something we derive right out of Bernoulli's equation here. And all he said was that so as the fluid flows into a narrower region of a pipe, the pressure goes down. And again, he was only looking at a horizontal pipe so that these potential energy per volume terms could be completely ignored, but that was the Venturi effect. It's something that's totally encompassed by Bernoulli's equation here. Let's take a look at one more. All right, so one last calculation involving Bernoulli's equation, and the diagram here is on the study guide. I wasn't expecting you to be able to come up with this diagram based on just simply the wording of the question, so I definitely included it. But the question says a horizontal pipe has a radius of 12.0 centimeters in region 1, but becomes constricted, reducing the radius to 4.00 centimeters before reaching region 2. The pipe in region 2 is also an average of 0.500 meters higher in elevation than the pipe in region 1. If the velocity of waters, so again we're identifying the fluid, and it says behaving as an ideal fluid in parentheses, flowing in region 1 is 2.00 meters per second, yet again, what is the pressure difference between regions 1 and 2? So it's another Bernoulli's equation calculation. And again, fortunately, we've done part of the work already. So because we've dealt with a radius of 12 centimeters going to 4 centimeters, so we already know the final velocity. And again, we can look at this and be like, oh, the radius is going to decrease by a factor of 3, which means the area decreases by a factor of 9, which means the velocity goes up by a factor of 9 according to the equation of continuity. And so if again, it's initially V1 is 2 centimeters per second. Let's do this in blue and be consistent. Well, then V2 over here is 9 times bigger and again is 18.0 meters per second. So again, fortunately, part of the work is done for us. And the big thing that's going to be different now is when we look at Bernoulli's equation. So these potential energy per volume terms are not going to be able to be excluded because there is a difference between the two areas of that pipe. So we'll have to include those in. So let's have a little fun here. But in this case, if we once again solve for P2 minus P1 over here, so P2 minus P1, which is the same thing as delta P. So I'm going to subtract P1 over to the other side, and then subtract these two terms over to this side. So we're going to have 1/2 rho V1 squared minus 1/2 rho V2 squared. So I'm doing this term and subtracting this one over, and then I'm going to have rho g y1 minus this term subtracted to the other side, so rho g y2, and that's equal to delta P here. All right, so now we can start plugging and chugging, and we're going to have 1/2 times 1,000 kilograms per meter cubed. So V1 again was 2 meters per second. Don't forget to square that. Minus 1/2 density of water, again, 1,000 kilograms per meter cubed. So times 18 meters per second. Don't forget to square that. So, and then this last part here. So we can probably combine some terms here and just do rho times g times y1 minus y2. Easier way to look at this. And so again, rho 1,000 kilograms per meter cubed, that density of water. So times gravity, 9.8 meters per second squared. And then it's really y1 minus y2. Well, y1 minus y2, well, y2 minus y1 would be 0.5 meters. y1 minus y2 is going to be negative 0.5 meters. It's just really the opposite of delta y, negative delta y, if you will. So negative 0.500 meters gets us delta P. So big, long calculation, but really no different than the last one, except that we've got the potential energy per volume term that we've also got to factor in. So now we'll let the calculator do a little work for us, or actually we'll take advantage that we just did similar calculations. So 4 times 1,000 times 1/2 is 2,000 yet again. So that's 2,000 Pascal. 18 squared again was 324 times 1/2 was 162 times 1,000 is 162,000, just like it was in the last one. And again, that's Pascal. So, and then this is going to be an overall negative term because of that negative 0.5. And so in this case, 1,000 times 9.8 is going to be, what, 9,800? And then times 0.5, it'd be half that, it'd be 4,900, and so minus 4,900. I'm definitely going to let my calculator confirm that, because I don't trust myself. All right, so 1,000 times 9.8 times 0.5 is indeed 4,900. All right. And so from here, I'm definitely just going to let the calculator do the rest of the work for me. So 2,000 minus 162,000, again, would be that negative 160,000. I put one wrong number in there. And then minus 4,900. And we get, this time, negative 164,900. I guess we should have known that, because if this was negative 160,000, then that gets us an additional negative 4,900. So in this case, then, that's delta P, and delta P equals negative 164,900. For 3 sig figs, we'll round that to negative 165,000 for that difference in pressure. Cool, that's as bad as the Bernoulli equation gets. But some of the principles you want to take home is just, again, like the Venturi effect, knowing that for horizontal pipe, if it gets constricted, the pressure goes down. And again, that seems a little counterintuitive, which is why it's important. You might be like, Chad, I'm used to like having higher pressures in my garden hose mean higher velocities. Yes, but you're not talking about any part of that garden hose having a higher pressure because it's getting constricted necessarily. You're just turning the water on higher and stuff like this. But you do want to take home definitely that if you go from a bigger region of a pipe to a smaller region of the pipe, the pressure does indeed go down as the velocity goes up, according to Bernoulli's equation. If you found this lesson helpful, consider giving it a like. Happy studying.